This is the PicoSystem from Pimoroni. It's a handheld games console based around Raspberry Pi's RP2040 chip, and today we're going to be unboxing it. I'm also going to show you a little project that I've been working on based around this, which if you follow me on social media you'll have already seen. But I'll leave timestamps in the video description, so if you want to skip the unboxing and head straight to that, then you can. I also want to apologise for being so quiet in the last few months. I actually moved to Germany at the end of September last year because I've got a new job out here. But as a result, I was preoccupied with packing everything up before that, and none of my filming equipment got here until early January. But I'm back now. I've got a bunch of videos in planning for the coming months, so with that said, let's get started. Like I said in the intro, the PicoSystem is based around Raspberry Pi's RP2040. This is the same chip used on the Pico board that I've showed off in previous videos. The RP2040 is a dual-core ARM Cortex M0 Plus microcontroller, which by default runs at 133 MHz, but I believe the PicoSystem API has it overclocked to 250 MHz. Alongside that, it has the RP2040's on-chip 264 kilobytes of SRAM and also 16 megabytes of flash memory from the external QSPI flash memory chip. So with that said, let's get this unboxed. So let's get this thing opened up. You can see there, PicoSystem on the top, made in Sheffield on the bottom. I love the 80s retro cyberpunk feel to this. And there you go, you've got the specs as well on the back. So let's have a look at this PicoSystem. I'll tell you what, it's a lot smaller than I thought it was going to be. It looks cool though. It's actually quite heavy. I guess that's due to the milled aluminium case. You can see that 1.5 inch display there. Take that off. I think the first thing to do is let's turn this on and see. So this comes with a game pre-installed. I haven't already opened this and added it. This is exactly how it came. But this is super square, bros. Player 1, player 2. And then you can see, well, this is the level. So there you go, level 1, let's go. And I'm terrible. Turns out this is actually quite hard to do when looking through a camera lens. Oh, I'm still terrible. You know what? Let's just turn that off. Firstly, I've got the little power button that goes in the top there. And then you can see there's a nice big battery inside there, which is a 525 That's a 525 milliamp hour battery, which is to be expected. And you can see this is actually one giant PCB on the front. I mean, it's kind of obvious anyway, because you can see that's obviously solder mask, silk screen, exposed copper, and then completely exposed just FR4 underneath the whole thing, which if you've owned any of Pimoroni's products in the past, then something like this silk screen and using exposed copper and stuff to make patterns, it won't be new to you at all. But it's actually a really thick PCB. I've never seen, I mean, I know PCB manufacturers make PCBs that thick, but I've never actually seen one. So, and then you can see there's that RP2040 right there in the middle. External flash, since the RP40 doesn't actually have flash built in. Buzzer, USB-C connector so that you can load your programs in, and it's also got the debug pins exposed, which is cool, so we could do something cool with that. And then finally the display connector as well, and obviously the battery, power button. That's the most interesting things that stand out. I'm guessing there's a bit of circuitry here with regard to the power button and how that works. Yeah, let's take a look. Let's have a look at the other side. So I have actually opened this before. I'd be lying if I said it. But I did look before, and you actually need to expose those screws to get to the front. So let's just Give that a wiggle out. And let's open up this. There we go. So there is the buttons and the back of the FR4. Interestingly, it looks like, if you sort of look there, it looks like this is a single PCB, but it's been milled down to a certain level. I could be wrong. It could be two PCBs glued together, but it's interesting the way they've done it. It certainly makes it easier than trying to use molded plastic or whatever to create a front. Got to be careful there so those buttons don't fall out. But yeah, you can see that there. Take those off. Exposed buttons underneath. Let's put that to one side. So let's have a look at the actual interesting bit itself. So this is the front bit, and honestly, all that's on it is that's a rear firing LED, which you can see there, or rather a rear mounted LED, and then the metal pads that allow you to click on each of the buttons. So those are kind of held in just with a bit of adhesive there that keep them on top, because underneath that will be exposed copper on the PCB that when you push, that'll make contact with basically the inner ring and the outer ring to create that, and then obviously the rubber pads just push through onto that. So there we go, looking good. And I'm not going to remove the battery because that's definitely held in with adhesive, and I don't want to make my own life too hard. So let's get all this put back together. There we go. And it still works, thank God, which is all any engineer wants when they take something apart and put it back together again. All good.
I've had this for a while now, and I was trying to decide what I could do with it. I've always wanted to create my own top-down 8-bit Game Boy style game, like Pokemon or Legend of Zelda. I've always been particularly interested in the original missing no glitch in the Pokemon Red and Blue games, and how exactly that bug happened with the way the games were designed. I think reading articles and watching videos that go into loads of details about the memory structure of the game and how the sprites were stored and rendered really gave me that itch to create a similarly designed game. To be honest, I'd love to design an actual Game Boy game in assembly using the same hardware, which is possible. You can buy programmable cartridges on Tindy, but I figure that's going to be a massive task, especially since I only learnt basic assembly back at university and haven't done anything even remotely similar since. So instead, I'll try it on modern hardware in C++, and if that goes well, maybe I'll look into doing it in assembly. The nice thing about the PicoSystem is that it comes with a MicroPython and C++ API, which takes loads of the initial work out of getting the hardware, the frame buffer, audio functions and graphic functions written. But for my purposes, I'm only interested in the bare minimum. So that's initializing the hardware and then getting a frame buffer working that I can easily write to, which will then be passed on to the display. The graphics library with the API is really good, and it contains loads of things for drawing shapes, rendering sprites, creating masks and blending colors and graphics, but the original Pokemon games never did any of this. They were drawing everything using tile maps and sprites, and I want to do something similar. If the need crops up later on, I can of course add things back in, but at the moment it's just taking up space in memory. On a side note, I got this up and running in Visual Studio Code using my own tutorial from last year, which surprisingly still holds up. It's just the only difference is it's now VS Code 2022 instead of 2019, and the chapters in the Raspberry Pi Pico Getting Started guide are slightly different, but otherwise it's still correct. The other nice thing about those top-down Game Boy games was that in general the player stayed in the center of the display and the map moved around them. And that's what I'm going to do too, since it's easier to write that than have a player who can walk around freely and then have to deal with the map having to scroll to keep them in view. So let's have a look at what I've done so far. I'm running the display with double pixels, meaning it's a 120 by 120 pixel frame buffer, which is split into tiles of 8 by 8 pixels, and thus a grid of 15 by 15 tiles. Sprites are stored in 2D arrays and are either 8 by 8 or 16 by 16 pixels, and then each sprite can be stored with multiple variants, so you just call whichever one you need at the time. Take the male player for example, we've got 6 variants of him based on the direction he's facing and if he's standing still or not. The sprite is then loaded into the frame buffer one row at a time into 1 or 4 tiles, always on that 15 by 15 grid. I looked at not using double pixels and having a 30 by 30 grid, but the 1.5 inch display is just too small, so I figured I'll leave it and save the memory. Things can be drawn off the grid, things like text and shapes, since the PicoSystem API was designed for that in the first place, but for me, designing the game I want, sprites will always be drawn on the grid. For the map, which is drawn first, we'll look at the size of the map and the player's position on that map, and then calculate firstly, how much of the map will be actually showing on the display, and secondly, how much blank space there is around it. I haven't written any code that stores unseen parts of the map in the frame buffer, so if you can't see it, it's just never read from memory. This might change later because at the moment when the player moves, the map moves one tile at a time, whereas although the original Pokemon games did the same, it actually scrolled each tile in rows and columns and pixels depending on how you're doing it. However, at the time when I was writing this, I spent ages figuring out the maths to render the map in the first place without causing memory issues, and I just didn't have it in me to implement scrolling, so it's definitely on my list of things to do when I'm up for the challenge of tackling low small vector mathematics, but not right now. The maps are also stored as 2D arrays, but there's a lot more information required for each tile, not just which sprite needs to be rendered. So we say whether players are allowed to enter that tile, so this is for like collision detection and stuff, but it's also split into each direction, because in Pokemon they had ledges that you could jump down, but then you couldn't climb back up them again, and I wanted to be able to implement the same kind of thing. We also determine how the sprite is rendered, which variant needs to be rendered, and then we can mirror sprites vertically or horizontally or both, which saves having to take up memory with the same sprites but facing the opposite direction or whatever. We then store whether that tile is what I'm calling an exit tile. So if a player is stood on an exit tile, we say which direction the exit is in, and if they step in that direction, they then exit the map. We then say what map needs to be loaded and what position the player will be standing up on the new map, and then we do a little fade to black transition, and then we switch over to the new map. That's all the code I've written so far, but the plan going forward is to figure out a way to make maps in a more friendly way. At the moment, I'm doing it all by hand in VS Code, and it's a huge ball ache. I know that there are map editors for tile maps out there already, but I just need to find a good one that will spit out the code I need in a nice format, or at least a format that I can run through a script to format it correctly or something. But if not, I'm just gonna have to write my own. But really the main challenge is figuring out what is the game I wanna make? What's the story? What's the aim? I've literally given it zero thought. All I've done is allow a player to move around a map. But I will be posting updates to this in the future, so get subscribed if you want to see how this goes. I'll leave a link down below to my Git repository if you're interested in seeing the code I've done so far. But otherwise, if you like the video, be sure to leave a like, leave a comment if you can think of a good game idea, and I'll see you guys in the next one.